Okay, so the last thing before we get into solving problems with exponents, it would be very, very helpful for you guys to familiarize yourself with some of the more common powers that we're going to see. So that means without using a calculator, you should be able to recognize certain things as being powers of 2. And which powers of 2? The ones with the exponents 2 to 10. So, for example, you should know that if you see 4, that's equal to 2 squared. Okay, you should know that if you see 64, that's equal to 2 to the 6th. So again, you should know all the powers of 2 all the way up until 10. Okay, the last one being 2 to the 10, which is 1024. Okay, similarly, you should know the powers of 3 that go up to the exponent of 5. Okay, the powers of 4 and 5 that go up to an exponent of 4, and any power of 6 to 12 up to it being squared. Okay, it's just really, really helpful because often you have to write things as a single power. You may have to be able to recognize certain things are powers of 3 or 4 or 2 or so on and so forth. Especially for those of you going on to 3U next semester, you're going to be doing some equation solving with exponential functions that, again, it's necessary to recognize that certain things are powers of others. Okay, so just keep that in mind as we move forward. So what I'd like us to do here is just practice using the different exponent rules and just express each of these as a single power. Okay, so I'll do the first couple with you, then I'll leave you to try the next ones. But let's say, for example, looking at this first one, we have 4 to the 3 times 4 to the exponent 7. Okay, and what this means is you have two powers multiplied together with have the same base. Remember, our rule says that if you're multiplying two powers the same base, you get to add the exponents. So it's the same thing as 4 to the exponent of 3 plus 7, which is 4 to the exponent 10. Okay. Now, normally from here you'd evaluate it, but I just wanted as a single power first, so there's no need to go any further from here. You can stop. Okay, for b, let's try the same thing. So we have 5 to the exponent 2 times 5 to the exponent 9 divided by 5 to the exponent 6. Let's do the numerator first. You have multiplying two powers to the same base. That's 5 to the exponent of 2 plus 9, which is 5 to the 11. So we have 5 to the 11 divided by 5 to the 6. Okay, when we divide these two powers with the same base, we subtract the exponents, we get 5 to the exponent of 11 minus 6, which is 5. Okay. What I'd like you to do now is try C and D on your own, and when you're ready to go through them together, push play, and we'll check to see if we're on the right track. Okay, so there's usually a couple ways of approaching these kinds of things. But let's take a look at C together here. So what I started off with first is I noticed that I had a power of a power here. So 3 to the 2, 3 to the exponent of 2, all the exponent of 5. So I can multiply those exponents together to get 3 to the exponent 10. And I did the same thing in the denominator here. I multiplied my exponents together, negative 2 times 3 to give me negative 6. Okay, so now from there, in my numerator, I have these, so two powers with the same base being multiplied. I add the exponents. 10 plus negative 4 is positive 6. Okay, I kept my denominator the same. And now I'm dividing two powers with the same base, so I have 3 to the exponent 6 divided by 3 to the exponent negative 6, which is 3 to the exponent of 6 minus negative 6, which is 12. So overall, this is 3 to the exponent 12. With D, you have a couple options here. What I find easier is to simplify as much as I can inside that bracket before I worry about this exponent outside. You could instead, if you wanted to, apply this exponent to everything on the inside, so to there, to there, to there, and to there. Okay, but that's a lot of work. So what I'm going to do, what I did instead first is I simplified inside as much as I possibly could so I wouldn't have to worry about doing all that expansion. So inside, I worked with the numerator first. So in the numerator I have 2 to the exponent 3 to the exponent negative 5. I multiply them together, so I add the exponents. 3 plus negative 5 is negative 2. And then I did the power of a power in the denominator here with this guy, which gave me 2 to the exponent 10. Okay, so from there, I then simplify the denominator, added the exponents, get 2 to the exponent 14. And then since I'm dividing two powers now, negative 2 minus 14 gives you negative 16. And remember, all along, all this is the exponent of negative 2. So then I have 2 to the negative 16, all the exponent of negative 2, multiply those exponents together, I get 2 to the exponent 32. Okay, so let's keep going. Let's try a few more. So 2 tells us to express 625 as a power of 5. So this is one of the reasons I wanted you to be familiar with a lot of different powers of some of the common bases you're going to see, because if you're expressing as a power of 5, you know that 5 to the exponent of something is going to be equal to 625. Okay, and if you don't recognize that this is 5 to the exponent 4, you're going to be doing some trial and error on your calculator. Okay, so if you really don't know, you can try different powers of 5, and you'll eventually get it to work after a few different tries. But again, if you recognize right off the bat that when you see 625, you know that's 5 to the exponent 4, you can save yourself a lot of time. Okay, so now let's start working a bit more closely with negative exponents. Okay, they showed up in these examples over here. We never had to evaluate them, so we could just use our exponent laws to simplify them away. But now we actually need to evaluate some of them. So let's look at 3 to the exponent negative 3 first. So remember our exponent law. This states that this is going to be the same thing as 1 over 3 to the exponent 3. So a general rule of thumb is you can take the reciprocal of the base and make the exponent positive. So 1 over 3 to the exponent 3 is 1 over 27. Okay, 3 cubed is 27. This is now evaluated. Okay, you should be able to do this without a calculator. Okay, so with b, we have negative 5 to the negative 2. So again, you want to deal with this negative exponent. One thing you have to be very, very careful of is that, again, this negative is not part of the exponent. Okay, the 5 is. If this negative was to be part of the exponent, it would be in brackets. So if it was in brackets here, then you'd have negative 5 all to the exponent negative 2. But that's not the case here. It's just 5 to the negative 2. So this negative is going to be left alone. And now, since we want to deal with a negative exponent, it's going to be 1 over 5 to the exponent 2. Okay, so now that negative again stays alone outside. 5 squared is 25, and we have our answer. Okay, if this was indeed negative 5 to negative 2, then you'd have 1 over negative 5 all squared, which would be 1 over positive 25, because here the negative would be squared as well. Okay, so it's important to know the difference between whether or not that negative is included as part of the exponent or not. Okay, let's keep going. So for c, now we have a fraction to an exponent. So again, the same rule applies. Take the reciprocal of your base. So instead of 1 over 4, it's 4 over 1, which is just 4. And the exponent now has become positive. So 4 over 1 is really just 4. So you get 4 cubed, which is 64. Okay, well, I suppose you can try D and E on your own, and if you want to give it a go. But let's just work through them now in case you want to keep going. So same idea here. Negative exponent. Here the negative is inside the bracket, so it's part of the exponent. So now we have 7 over negative 4 all squared. Okay, and this doesn't simplify very well, not if we want to avoid decimals. So what we can do now is remember, if you have a fraction to an exponent, you can apply the exponent to both the numerator and the denominator. So this is the same thing as 7 squared over negative 4 squared, which we can then simplify. So 7 squared is 49. Negative 4 all squared is positive 16. Okay, and last but not least, e. You can try plugging this in your calculator, but I'll bet you're going to get some sort of ugly error because the numbers are far too big. What you need to watch out for here is you see how the exponent is 0. And remember that anything to the exponent 0 is equal to 1. So this whole thing, as ugly as it is, just equal to 1. Okay, a couple things I just want to talk about with the exponent of 0 being 1. Remember that only anything to the exponent 0 is 1. Let's just say I had 2 times 17 to the exponent 0. That doesn't mean the entire thing is 1, right? Only the 17 is part of that exponent is put to the exponent 0. So 17 to the 0 is 1, but then you still multiply it by 2 and you get 2. Just be very, very careful. Don't just automatically assume if you see an exponent of 0 that the answer is 1. Everything that has that exponent is 0, but if there's anything else laying around, you still have to treat that accordingly. Okay. A couple more types of examples, and we'll be done. So now we have something that has negative exponents in it, and as a rule, you tend to not want negative exponents in a final answer. They don't look very pretty. So you want to express things with positive exponents. So here's something, a to the negative 3, b to the 7, c squared d to the negative 4. We want to express it with positive exponents. So I'm going to go through this one a little bit slower just to show you what's actually happening. Eventually you'll see a bit of a faster way to to get from the question to the final answer. But I'm going to write this out in a longer way, saying this is going to be a to the negative 3 times b to the 7 divided by c squared times d to the negative 4. So I haven't changed anything. I've just rewritten it with, instead of a fraction, using division. And I'm going to evaluate all these separately. So a to the negative 3 we know is 1 over a cubed. Okay, b to the 7 is just b to the 7. Okay, and over from our denominator here, I'm going to have c squared. And d to the negative 4 is 1 over d to the 4th. Okay, and now what I'm going to do is I'm going to simplify. So b to the 7, remember, just b to the 7 over 1. So if it multiplies in the numerator here, so I get b to the 7 over a cubed divided by the c squared multiplying into here gives me c squared over d to the 4th. Okay, so what I have now is just two fractions that are being divided. Well, how do I divide two fractions? I multiply by the reciprocal. So let's give us some more space here. So if I was going to actually divide these, this would be the same thing as b to the 7 over a cubed times d to the 4th over c squared. Okay, and then I can just simplify this by multiplying the numerators together, multiplying the denominators together. So this becomes, multiplying the numerators together, b to the 7 times d 4th. Do the exponent 4, and then you have a cubed times c squared. And now everything has positive exponents in it. Now, you might be able to see, if you look at the final answer and the original question, a little bit of a shortcut here. And you might be a little bit mad that we did all this work, because you can see that if you just move the d to the negative 4 up to the numerator and made the exponent positive, and move the a to the negative 3 down to the denominator, made the exponent positive, you get the exact same answer. And that actually is the case. Okay, so you don't have to go through all this work every single time. It's important for you to see why it works out the way it does. But as a bit of a shortcut here, you can move negative exponents from numerator to denominator as long as there's no addition and subtraction between them. As everything's multiplied, you can move things freely from numerator to denominator and vice versa and have the exponents change from positive to negative. Okay, okay, so now, with a couple more examples to go here, I want you to look at number 5. It says express as a single power first and then evaluate. So you can't just punch in your calculator and just put that as a final answer. You have to be able to show that you know the exponent laws and simplify it by expressing as a single power first. Okay, so looking at number 5, we have 3 to the negative 2 divided by 3 to the 4. So let's use the exponent laws to simplify this. So subtracting the exponents, we're dividing powers of the same base. This is the same thing as 3 to the negative 6. So we've expressed as a single power. Okay, and now we need to just evaluate it. So it's going to be 1 over 3 to the exponent 6. Okay, 3 to the exponent 6 you can figure out in your calculator. It's 729. So this whole thing is 1 over 729. Okay, B. Okay, so B have a bit of a problem here because these bases are not the same. So right now there are no laws that you've seen that you can use to simplify this to express as a single power. So the trick here is, and again, it's important to recognize if numbers are powers of others, because 4 is the same thing as 2 squared. So what we can actually do is rewrite this as 2 to the exponent 13, but instead of 4, we replace 4 with 2 squared. And again, that's all the exponent 5. So by doing this, now I have everything in terms of base 2. So now I can have 2 to the 13 up here. My denominator using power of a power rule is 2 to the exponent 10. So I have 2 to the 13 divided by 2 to the 10 simplifies into 2 cubed, which is equal to 8. Okay, so again, really, really helpful to recognize if certain things are powers of others, because sometimes you can put things all in the same base. Okay, so almost done. A couple of examples left. Take a look at them yourself first and try and simplify them as much as you possibly can, and we'll finish them up in part 3.